Hi everybody, welcome to another video in Precalculus, section 8.7, the cross product. So now we define the cross product. Let V, vector V, vector of three components A1, B1, C1, and vector W, three components A2, B2, and C2. The cross product of V cross W is defined as follows. Well, if we just stick to the definition, it would be difficult to try to memorize it. There's the reason it is this way, but if we just memorize it, it will be difficult. Notice that number one, the product of the cross product here is going to be the vector. It also have ijk component, and because of this, it is sometimes referred to a vector product. Right. One distinction between this and the dot product is that the dot product will work for any dimension vectors, 2 dimension, 3 dimension, any vectors. The cross product, the way we define this, only works for 3-dimensional vectors. For 3-dimensional vectors, or just say 3D vectors, and the product of that is also a 3-dimensional vector. And so where's this come about? How do we write the cross product like that? Right, first review determinant, and determinant, it is at the end of course algebra. We use determinant to solve the system of equation, but of course it have a lot more use than just that. Right, determinant, if we have a 2x2 determinant and we just want to take the product of this diagonal northwest southeast diagonal, we take the product A1, B2, and then we subtract the product of the other diagonal. So that's what we have. So 2x2 is easy enough. Now for 3x3, there's a lot of different way to evaluate a 3x3 determinant. What we do here is using the cofactor or the minor expansion. So the thing is, we can pick any row or any column. In this case, we will pick the first row. So then we have A, B, and C. Right. Once you pick the first row, the sign chart associated to that, kind of like the chessboard, plus, minus, plus, minus, plus, minus, plus, minus, plus. Right. So the sign will be, for the first row, it's going to be plus, minus, and plus. So it's going to be plus, minus, and then plus. Right. Now if we use the second row, it will be minus, plus, minus. Right. Once we do that, then we just go over the row and the column that containing A, B, and C. Now multiply by A, we go over the row and the column that containing the point A. So we go over that row and that column. We left with B1, C1, B2, C2, and that is 2x2 determinant. That's easy, just evaluate that. For B, go over the row and the column that containing B, A1, C1, A2, C2. Find the determinant, 2x2, easy. And then for 3x3 determinant, for C, go over the row and the column, and that's what we have. Find the determinant 2x2 here. Once we have that, just evaluate. That's simple enough, right? Let's just look at this example. Find the determinant of the following matrix 1, 2, and negative 3 and 5. So this diagonal 1 times 5 minus the product of the other diagonal. We have 5 plus 6, that is 11. Right. Now 3x3 determinant. First I'm going to take this row. And for the first component, which is 1, if we cover the row and the column, what we left is the 2 by 2 determinant 2, 1, 3, and 6, and multiply by the element, which is 1. And remember the sign is plus, minus. Next component is 3, so we cover the row and the column that contain in 3. We left with the 2 by 2. And that was 3, but with the minus. And then we're going to add that -5, cover the row and the column containing -5, -5. Right, so we do that. And 2 by 2 determinant 2 times 6 minus 3 times 1 times 1, which is itself, minus 0 times 6 minus 1 times -6, whatever we have, times 3, and then plus 0 times 3 minus 2 times -6 times -5. Right, 2 times 6 is 12, minus 3 is 9, minus 0 minus -6, so this is positive 6 times 3, so 6 times 3, and then plus that's 0 minus, so that is 12 times -5. So we have 9 minus 18 minus 60, and that is 9 minus 18 is -9, -69. Right, so that's what we have. Now, of course, we can evaluate this along any row, any column. So let's do that differently. Now, by the way, the determinant, we use the straight bar instead of the bracket. The bracket is the matrix, 2 vertical bar is determinant. Now, instead of evaluate along that column, that row, I can evaluate along this row, which is perfectly fine. F0, 2, and 1. Evaluate along that row. But that row, we carry the sign negative, plus, negative. So it's going to be negative. Right. Cover the row and the column that containing 0. So we have 3, -5, and 3 and 6 times 0. And then the sign is going to be minus, plus. Cover the row and the column containing 2. So we left with 1, -5, and -6 and 6. And then we plus, cover the row and the column containing 1. We have 1, 3, -6, and 3. Right, to evaluate, anything times 0 is 0. 1 times 6 is 6, minus -5 times -6 is plus. Minus 5 times -6 is 30, but subtract that direction, times 2, plus 1 times 3 is 3, subtract the other direction, -6 times 3 is -18, subtract -18. Right. So 6 minus 30 is minus 24. Okay. And this should be 3, right? Let's do that again. for 2, so 1, -5, -6, 6. The first one doesn't matter, and then 1, -5, -6, and 6, and then for the last one, 1, 3, -6, and 3. So 3. That okay. What we have, right? 6 minus 30, -24 times 2, -48. And the sign will be minus plus and minus. Sorry about that. And then 3 and 18, -21. I mean subtract 21, and that gives us -69. Right. So whether we evaluate along the first row or any column is fine. The concept still the same. We cover the when we take out the only entry in that row, make sure the sign will be corresponding to the sign chart. Since we pick the second row, the sign will be negative, positive, and negative. Right, and then we just write with respect to that element, cover the row and the column, and we have the sub matrix. Of course, with this way we can find the determinant 4x4 in higher dimension. Right, but first let's just go to the cross product of VW. Now, once we write like that, the cross product of VW will be just determined to be the determinant of. I will write that. It's easier to write than to describe it. Right. So vector V cross vector W. So this will be the determinant. We have I, J, K on the first row. V will be on the second row. And then 3x3 determinant should be easy, right? For component I, we left with, just say, for I do everything with respect to the first row. So cover the first column, the first row, with respect to I, we left with 2, 9, 3, and 4. And then multiply by vector I. And then subtract for J. We have 6, 9, 2, and 4 for J. Then for K, 6, 2, 2, 3, K. So 2 times 4 is 8, minus 27 I, minus 6 times 4, 24, minus 18 J, and 6 times 3 is 18. Let's work back to 18 minus 4 K. So that gives us on the first component A minus 27, that minus 19. 24 minus 8 is 6 with a minus. 18 minus 4, 14. So this is the cross product of V dot W. So we just find the determinant. The first row is IJK, the second row is the first vector, the third row is the second vector. We just do the 3x3 determinant. Right. Let's do more example. V cross W. So V cross W is equal to first vector is always IJK. I mean the first row is the vectors IJK. Vector V 6, 2, and 9, 2, 3, and 4. Six, 2, and 9, 2, 3, and 4. Actually, we just did this on the previous page, and we have that negative 19, negative 6, and 14. Right, did that. Now, W cross V. W cross V, first row is the component, the component vector ijk. Second row is vector W, 2, 3, and 4. And then 6, 2, and 9. Right. Again, evaluate along the first row. For the first row, cover the row and the column that containing I. We have 3, 4, 2, and 9. That is what I just say in the I component. And then next, we have 2, 4, and 6, and 9. That in the J component. But the sign will be minus. And then we have plus 2, 3, 6, and 2 in the K component, and that is a plus. Right, so 3 times 9 is 36, minus 8. But do the math correctly. 3 times 9, 27, minus 8 in the I direction. Subtract 2 times 9 is 18, minus 24 in the J direction, and plus 2 times 2 is 4, minus 18 in the K direction. 27 minus 8, that's 19. First component. Second component, 18 minus 24 minus 6 with an extra minus gives us positive 6. And then 4 minus 18, that's minus 14. So that is W cross V. So what we see here is V cross W, W cross V. You see they're opposite to each other. So here notice that V cross W is equal to opposite of W cross V. Right. Now let's find vector product of V and itself. Vector V, with the first row of course I, J, and K. Vector V is 6, 2, and 9. Vector V also 6, 2, and 9. Right. With respect to I, cover the row and the column. We have 2 and 9, 2 and 9. By the way we write it, do not put a comma in between. Just give some space in between. For which the I component. Subtract 6 and 9, 6 and 9. The J component. And then plus the size, plus, minus, plus. Six, 2, 6, and 2. Okay. Right. Now you have 2 times 9 times 2 times 9, so 18 minus 18 in the I direction, minus 6 times 9, 54 minus 54 in the J direction, and then plus 6 times 2 is 12 minus 12 in the K direction. So pretty much we have the vector of 0, 0, and 0. Or we say this is a 0 vector. Right. So we have another note. Any vector cross with itself is equal to a 0 vector, not a 0 number, because this is a vector product. The product is going to be a vector. Now we have these properties. Algebraic properties of cross product. Now, any vector cross itself is equal to 0 vector, because we have that. Vector is not commutative. If we cross u cross v is equal to negative v cross u. So if we change the order of the vectors, if we change the two rows in the determinant, we're going to have the opposite to what we have. And then distributive properties, we still have that. So that is the algebraic interpretation of the cross product. Now the geometric properties of the cross product. U cross v is orthogonal to both u and v. So because we have this kind of in the previous section, let me zoom out. If we have three vector, first vector, the second vector, then when we determine the direction of the third product, remember this is the vector product, the product is the vector. So to determine the direction of the product vector, we use the right hand rule. Right hand rule say put the hand in the first vector, curl the fingers in the second vector, the thumb will give us the third dimension, give us the direction of the vector product. So or we just say put the first vector and then curve. So just first vector and then curve that in the second vector. Do not switch the fingers, of course. And then the third finger is the product. So this is the right hand rule. Now if we turn this backward, the first vector, the second vector, and then that will point down. Right. So if we interchange the order of the vector, we cannot change the fingers. We can only flip it like this. And then the vector will point in the opposite direction. So that is what we have, the right hand rule. So the index finger in the first direction, the middle finger in the second direction, the cross product is the thumb. So that gives us the direction of the product. Now, remember, the first part where you define vector has two components, the magnitude and the product. The magnitude and the direction. We have the direction as defined as the right hand rule. Right. Now, what is the magnitudes? So the magnitudes of u cross v is determined to be the product of the magnitude times sine. If it is the dot product, it's going to be cosine. The cross product is going to be sine. And then, but even better than that, the interpretation is that u cross v is the area of the parallelogram formed by u and v. So if we have the vector u and the vector v, the area of that parallelogram is given by the magnitudes of u cross v. It has to be the magnitude, because if we don't have the magnitudes, we have just a vector. Of course, vector have direction and magnitude. We only want magnitude, so that's why we put the magnitude. And then u cross v is equal to 0 vector if and only if they are parallel. If the angle between them is 0 or 180 degrees, sine of 0 or 180 degrees is 0. So if sine equal to 0, the magnitude equal to 0, therefore it has to be a 0 vector. Right. Now, let's do this. Let's find the cross product of I cross j. Of course, ijk is the component. I is 1, 0, 0, and j is 0, 1, 0. So 1 in the x direction, 1 in the j direction. So what is the cross product? Well, just do it. I, j, k, 1 0 0 0 1 0. Right. When we get used to this, we just do that for I 0 0 1 0 in the I direction. For j 1 0 0 0 j direction, plus 1 0 0 1 in k direction. So what we have is 0 subtract 0, so we have 0 first component, and 1 times 0 is 0, subtract 0, so 0 for the second component, 1 subtract 0, and this of course is equal to k. So the first is that vector I cross vector j is equal to vector k. Now we have the previous section. If we interchange them, j cross I will be equal to what? If we change the order of the vectors in the cross product, we have the opposite vector. Now that makes sense. That's what the right hand rule come about. If we have the right hand rule, the first vector in the I direction on the x-axis, second vector in the y direction or the j component, and then the third vector is in the k component, because the third vector is perpendicular to both of them. Perpendicular to both x-axis and y-axis has to be the z-axis, and the right hand rule will determine the positive z-axis, which is k. Right? And then finally, the magnitude. Magnitude of 1 times magnitude of 1 times the sine of 90 degrees. Sine of 90 degrees is 1. So in fact, I cross j, if we want the magnitude, we have the magnitude of I, which is 1, the magnitude of j, which is 1, the sine of the angle between them, sine of 90 degrees, is 1. So this is equal to 1. So that's why the direction is equal to in the positive z-axis, and the magnitude is equal to 1. So that's why we confirm that both algebraically and geometrically. Algebraically, this is what we do. Geometrically, we use that the magnitude is 1, the positive direction, the direction is positive z-axis. So that's what we have. And then j cross k, I think we just need to do one more, then the last one will follow easily. Right, j cross k, j will be on the positive y-axis, k positive x-axis, I mean positive z-axis, 0 0 1. So cross product I j k 0 1 0 0 0 1. So in the I component, I for j 0 0 0 1, and for k 0 1 0 0 k, and this is the first one's 1 minus 0, so 1, 0 minus 0, and 0 minus 0, and this of course is the vector I. So what we have here is j cross k is equal to I, and if we reverse the order, k cross j will be equal to negative I. Simple enough. Now, if we do the same thing, k cross I will equal to j. I mean, we do the same thing. It's not that difficult. Equal to j. So we have k cross I is equal to j, and if we reverse them, I cross k equal to negative j. And then of course we have all of those. I cross I equal to 0 vector, j cross j equal to 0 vector, and k cross k. And the vector cross itself is equal to the 0 vector. So put all of that together, we have this cyclic relation I, j, k, back to I. So I cross j is equal to k, k cross I equal to j, and j cross k equal to I. Wait, I cross j equal to k, j cross k equal to I, and k cross I equal to j. So we just go around and around. If we go reverse, it's going to be negative. And the vector cross itself is equal to 0 vector. Alright, now let's do this using a different way. Now, v cross w. So I will write v cross w. I will write ijk component 6 I 2j and 9k. That cross with 2i 3j and 4k. Now I will multiply it out, 6i and 2i. So I multiply the numbers and then cross the vector. So 6 times 2, that's 18 I cross I. Right, now 6 times 3, 6 times 2, uh, 6 times 2, that we have 12i cross I. Right, 6i and 3j, that gives us 18i cross j. 6 times 4, 24i cross k. That's the first one. Next, I'll go to 2. For 2j times that, I'm going to plus 4j cross I plus 2 times 3 is 6 j cross j. 2 times 4 is 8 j cross k. And then next we have 9 times 2i, 9k times 2i is 18k cross I. 27k cross j, and 36k cross k. Right. Now, next what we have is the vector cross itself is equal to 0 vector. So this is equal to 0 vector. So this is just 0 vector. This is also 0 vector, and this also 0 vector. So we have all of those are 0. Next, I cross j is what? It is k. I cross j equal to k. I cross k, this going backward, is negative j. J cross I also backward, negative k. J cross k is equal to I. K cross I, yes, that is j. And k cross j, that backward, negative I. To put all of that together, we have 0 vector because we don't need to write that. but what we have is 18k minus 24j minus 4k plus ai and plus 18j minus 27i. And then just combine like terms. For I, 8 minus 27 minus 19i. J, negative 24 plus 8, negative 6j. And for k, 18 minus 4 is 14k. If we compare that to the first one we did, where we use the 3 by 3 determinant, we have negative 19, negative 6, and 14, which is the same thing, right? Yeah. But doing like this seems like a lot of work, especially we have to write the vector as a boldface. But that certainly works. Right. Now, as to this example, I'll find a vector that is orthogonal to u and v. Well, how do we do that? If we have a vector u and the vector v, they're not orthogonal to each other, which is fine. Now, we find the third vector that is orthogonal to both. So simply, we just do the cross product. And then we say, do we do u cross v or v cross u? The answer is, it doesn't matter. If we have u cross v point up, if we want to interchange the direction of the vector, it will point down. So either way, we have a vector that is pointing up or a vector that is pointing down. Both of them will be orthogonal to the plane contained in the u and v. So in this case, usually we just cross them, u cross v. In that case, we give a vector that is orthogonal to both of them. They don't have to orthogonal to each other. Yeah, of course we can do it like this, or we just have like this. But if both of them in the same direction, then we don't know if it can rotate. So that's why two vectors like this, we cannot determine the third vector because it can rotate. It will. Right, anyway, if we want to find a vector orthogonal to both vectors, we just cross them very much. 6, negative 2, 9. 5, 1, negative 1, 4. Right, for I, negative 2, 9, 1, negative 4 in the I direction. For j, subtract 6, 9, 5, and negative 4 in the j direction. And k, 6, negative 2, 5, and 1, k. Right, negative 2 times negative 4 is 8, minus 9 in the I direction. Subtract negative 24, 5 times 9, negative 45, j, and 6 minus negative 10, minus negative 10 is plus 10, k. So give us negative 1, I, 24 and 45, that's 69, negative 69 with the minus, that's plus 69, j, plus 16k. So -1, 69, and 16. Right, so that's what we have. Right, next, note, suppose U and V are adjacent sides of a parallelogram, then the length of this side are U cross V, and if the theta is the angle between them, then the height of the parallelogram is given by this. Bottom line is the area of the parallelogram is going to be U cross V, the magnitude of U cross V. So that's simple enough, right? Now, if we want the area of half of it, which is a triangle, if we just write the area of the triangle, the area of that triangle containing vector U and V is going to be half of that. So I will write area of triangle with side U and V is, it's going to be half of the area of the parallelogram. So it's have 1/2 magnitude of U cross V. Right, if we want the whole parallelogram, U cross V, take the magnitude. If we want the area of a triangle, cut it in half. Right, now here's an application. Find the area of the parallelogram whose vertices are 1, 2, and 3. So we have those vertices. And just let's draw a sketch. By the way, we assume that this is in the order P1, P2, P3, and P4, and not twisted. It is not twisted like P1, P2, P3, and P4. We assume that it is go in either clockwise or counterclockwise, doesn't matter. But P1 is opposite on P3 and P2 is opposite from P4. Right. Now, in that case, what we need is we can say, let's say P1, P2 is a vector U, and P1, P4 is a vector V. So first, let's find the vector P1, P2. P1, P2, of course, the end point minus the initial point. P2, 5, -4, and 3 minus initial point of 1, 1, and 1. Now it is a vector. Of course, the notation for the points is that, but when we subtract them, we have a vector. So we just switch the notation to a vector. 5 minus 1 is 4. Minus 4 minus 1 is minus 5. And 3 minus 1 is 2. So that is P1, P2, which is U. Now, V is P1, P4, 4 minus P1, P4, 3, 2, 1, minus P1, 1, 1, and 1. Of course, we don't want to use P1, P2 cross P1, P3 because it's not, we're not doing the diagonal. We use two adjacent sides. So that gives us 2, 1, and 0. Right. So, and finally, the area of the parallelogram, we just do the cross product of these two. Don't forget, at the end, we take the magnitude. So, area is equal to U cross V magnitude, or magnitudes of P1, P2, cross P1, P4. Right. So, just do this cross product. P1, P2, cross P1, P4. By the way, we could also do P1, P4 cross P1, P2, meaning we can interchange of this. If we don't want to do U cross V, we can also do V cross U. but at the end we take the magnitude, so it's still the same, right? Because opposite vectors will have the same magnitude, it just have opposite direction. Right, so cross product of these two, I, J, K, right, 4, -5, and 2, 2, 1, and 0. So for I we have -5, 2, 1, and 0 in the I direction. For J, 4 and 2 and 2 and 0 in J. And for K, 4, -5, 2 and 1 in the K direction. Right, sorry. I, -5, 0, 1, 0, -5, 2, 1, 0. For J, 4, 2, 2 and 0. And K, 4, -5, 2 and 1, K. Right. -5 minus, -5 times 0, 0 minus 2, 0 minus 4, and 4 minus -10, so give us the vector -2, negative and negative, that's a +4 and 14. Now we just find the magnitude of that. So the area of parallelogram P1, P2, P3, P4 is equal to the magnitude of, we did say P1 cross P1, P2 cross P1, P4. So the magnitude of this, -2 square +4 square +14 square. -2 square or just 2 square, same thing. 4 square and 14 square. So we have square root of 216. Right. So the area of P1, P2, P3, P4, the parallelogram is that. Of course, we can use P1, P4, and then cross P4, P3. Any two adjacent vector will be fine. Direction, I mean the order of U, cross V or V, cross U, doesn't matter. But we just pick two adjacent vectors, do the cross product, take the magnitude. That gives us the area of the parallelogram. Now, if the question asks us what is the area of the triangle P1, P2, P4, then we say the area of P1, P2, P4. So of course that will be half the area of the parallelogram, right? It's going to be half of P1, P2 cross P1, P4. Be half of that. Right. So whether we ask to find the area of the parallelogram or the area of a triangle, we still do the cross product. Take the magnitude. If we want the area of a triangle, cut that in half. But make sure that the point actually have to go in the order, maybe clockwise or counterclockwise. We don't want to do the cross product of a side and the diagonal. We want the product of two adjacent sides. Right. So that's what we have for cross product. So in cross product, it is a vector product. So the result is going to be a three-dimensional vectors. By the way, I did mention that cross product only works for three-dimensional vectors. Four-dimensional vector will not work. Two-dimensional will not work. And we use determinant to find the cross product. these properties are important. If we interchange the order of the vectors in the product, we have the opposite to that vector, opposite of the product distribution. Right, not really important. Now, the cross product is a vector, right? A vector has direction and magnitude. So the direction is given by the right-hand rule, and the magnitude is given by the area of the parallelogram of the vector u and v. And then we have this cyclic rotation. I cross j is k, k cross I, j, and j cross k is I. So just go in that circle. If we go in reverse, this is going to be the opposite to that, like I cross k is equal to negative j, for instance. And any vector cross itself is equal to a zero vector. I don't recommend you to do it like this though. And finally, if we want a direction, the cross product of two vectors gives us a vector that is orthogonal to both of them. So this product is orthogonal to a plane containing these two vectors. So that gives us the direction. And finally, the magnitude is the area of the parallelogram. And here we have an example. If we want the area of a triangle, just cut that in half. Right. With that, I finished section 8.7. Always, thank you for watching, and see you in another video in pre-calculus.